Thanks to the Talk Python team who sponsored this episode of the Engineered Mind podcast. If you want to learn Python and delve into exciting topics like data science, web development, or building apps, feel free to visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience and other interesting topics to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I'm very excited to welcome David Josephs to my show. David studied aerospace engineering and astronomy. He's an aspiring data scientist, vivid open source contributor, chess player and ML researcher. His interests go from explainable models to time series, over parametrized deep learning, and a lot of other exciting topics like RL and Myoelectric Control to map brain signals in the body to motions in the extremity to control prosthetic limbs. In this podcast we talked about XAI, if deep learning is alchemy, artificial general intelligence, and a variety of other topics. For updates on upcoming podcasts, projects and videos, make sure to follow me on Twitter as well as on Instagram. To join our weekly newsletter engineeredmind.sh, where I share exclusive content, visit yusef.substack.com. And now, ladies and gentlemen, here's my podcast with David Josephs. Hi David, welcome to my podcast. Maybe as always, we get things started by introducing yourself. So maybe do that.
All right, yeah. So hello everyone. First of all, thanks for having me. I'm really excited to be here. So I'm David Josephs. So I started out as an aerospace engineer, and then I studied astronomy. And then I realized what I was really interested in was machine learning. And so, now I've just finished my master's focusing on machine learning. And, now I'm looking to, get into PhD programs so I can continue to, study what I love to do. Really happy to be here.
That sounds good. What will you do in your PhD program? I think it's focused on reinforcement learning, right?
That's something I'm trying to figure out still. But really, I think, it depends on what's interesting for the field as a whole. But so reinforcement learning is definitely something that's really interesting, as well as, being able to explain reinforcement learning, at a deeper level, not just at a surface level, is another really kind of fascinating topic. And then also one thing that I'm really interested in is the combination of the theory and the application of machine learning and deep learning, where theory informs application, application informs theory. I think that's a really interesting little, that's very broad, but a really interesting subfield that would be fun to research for, a really long time.
Mm-hmm. What fascinates you the most about artificial intelligence? Not only reinforcement learning, but maybe something specific.
I think it's really the ability of, especially with deep learning, because, I lucked out to come into the field right when deep learning starts, exploding, which is really exciting. But the way that we can, take something as complicated as an image, which is, hundreds or thousands of pixels, and turn that into represent that in 300 numbers or something like that. The ability that we can take a large amount of information and compress it to a small amount of information is just really cool and really exciting.
Mm-hmm. Do you think by studying reinforcement learning, because there's this parallel, right? We are somehow agents submerged into an environment. Do you think by studying reinforcement learning, this will definitely bring us more towards AGI?
AGI is a really tough thing to reach. I think what we can reach with within the next 5 or so years wouldn't be general intelligence, because I think that's the other thing. The more you look into this stuff, the more you realize oh wow, this is kind of dumb. But so I think but we can develop really good, I would call it, I don't know, it's never been talked about before, but ASI, artificial specific intelligence, where you have a set of agents who are really good at solving specific problems. And I think that's potentially just as useful, because I don't think really there's a big difference between having one entity which understands everything really well versus having hundreds of different smaller entities which you can use for specific tasks. And I think that's where we'll probably end up first before we reach AGI, because I think that's, a longer way off, because there's still some fundamental issues we have to deal with.
Definitely. And I think when we go towards AGI, there's always this thing where we try to find the counterpart of a human being, right? So if we decide for something, why did we take this road? We somehow cannot explain it, but it's kind of in the like unintuitively we do it. So that's where explainability comes in.
Yeah, exactly.
And you worked on that, right? Can you maybe explain the audience a bit what is XAI and how can we approach this?
Yeah, so XAI, the idea is taking something that's typically, there's two types of models in like machine learning in general, or there's a bunch of different ways you can classify models, but really you have, simple models which we can intuitively understand and explain, and which would be, for example, linear regression or a decision tree, where we can even like visually see how it's making decisions. And then we have more black box models, which would be like a support vector machine, or deep learning would be like, a very big example of something that's not like inherently explainable. And the idea of XAI is to take these things that aren't explainable, for example, deep learning, and make them explainable. So the idea, I was preparing for this, and I was the idea of something being explainable which isn't explainable. So for example, deep learning, we can't actually explain deep learning because the problem is we don't really even understand fully how it works or why it works. Because you take this thing which has potentially millions or billions of parameters, and you feed it just millions of data points, so you have more parameters than data points, and somehow contrary to like all of our statistical beliefs, where we think the less parameters the model has, the more it'll generalize. Conversely, with deep learning, we'll see that the bigger models actually can generalize better and extrapolate to newer data, which doesn't make any sense from a statistical perspective. So we don't really know why it works still. So we can't just say, oh, it made this decision because of this. So finding ways to show that it's learning something meaningful to a human. So that means, like, for example, if you were trying to learn dogs versus cats, you want to see that it represents a dog in a different way than it represents a cat, like across all the dog images and all the cat images. Or with the concept of like a self-driving car, which I think we might be a long way off of, seeing that like it notices a stop sign, but it also notices, or let's say it notices a green light, but it also sees someone crossing the road. You would want to see that it weighs more importance on the person crossing the road than the green light. If the other way was true, that would be really bad. So making decisions based off of things that we understand is one way. Then the other thing is, for the widespread acceptance of especially complicated models like deep learning, for someone like me, or someone who's studied machine learning a lot and who like trusts them and has done all the math, we don't like. I trust it sometimes, but if you were trying to show your boss, like, hey, look, I did this thing, and he's like, oh, well, this is what I've done for 20 years. Like, why is it doing this? You better be able to tell your boss, like, why it's doing this, because this could cost them a lot of money. So I don't know where I was going with this, but yeah, I think, you want to make something, take something that's a black box and make it something that you're confident in, something that you can trust, and something that you feel safe using. So that means it won't do something just like, it doesn't have to be 100% accurate, but, when it goes wrong in an expected way. Is another, something related to explainability, but really it's just building trust and confidence in black box models, so that way they can be, accepted and used in the real world for real problems. So for an image classification problem. So in the show Silicon Valley, there's like a really funny episode where they're making this image classifier for all images or something like that, and they show the app and it's hot dog versus not hot dog. And for hot dog versus not hot dog, interpretability and explainability doesn't really matter. That's not a problem that could impact your life. But for example, if we're using some sort of model to like model sentencing, for criminals, you know, then you'd want to know why, like it's giving one guy, a 20-year sentence versus another guy a 5-year sentence,
Yeah.
right? Because I mean, law, you inherently have to give explanations because it's like almost an opinion-based field. Same thing within medicine. Like if you're trying to decide whether or not someone is at risk for, a disease, um, you'd probably want to know that the reason that that a person's at risk is something that like agrees with the common like medical understanding of the world. So in those cases where we're putting something like AI or machine learning in, applications that have impact on people's like, big impact on people's lives, you definitely want to have a, high degree of interpretability, which, you know, that's hard to attain, which we can talk about more. Yeah.
There's this cool article which you shared with me, which I can also link down in the description. This debate between Chomsky and Norvig. If you want, you can go a little bit into detail there. What is science and how we can explain things.
Oh yeah, yeah. So there is, there's this ongoing debate in the whole field of machine learning of whether what we're doing is, science, or there's a classic debate. I can't remember who the guy on I can't remember one of the names, but so it's between it was at NeurIPS, which is like this big machine learning conference in 2017, and the debate is AI and especially deep learning, is it alchemy or is it science? Which alchemy, it's just like magic and it just works sometimes, and science is exactly how we view science, like experiments, and it's well thought out. And so this debate between Norvig versus Chomsky kind of preceded that. And what Chomsky is arguing is that basically, we're not really doing science, because what we're doing, if we're fitting like a statistical model or a deep model, just some sort of black box to something, we don't really have an understanding as to what it's doing. Whereas if you look at physics or any other field of science, you see that they're developing rules and theories, instead of just black box, like my model says this, so it's how this is. The probability of this word is 0.75. So that's kind of a debate that motivates. So one thing, using, a deep neural network or, any sort of machine learning or AI thing in practice, that could be viewed as almost an engineering problem where we're trying to, just use this thing and we're going to solve the problem. We're going to figure something out with it. But, if we want to, one thing, I also think about this with reinforcement learning too. One thing that hasn't been explored as much is using these deep neural networks and, other algorithms to further our understanding of the world. So for example, in chess with AlphaZero, which, is the coolest thing ever, right? Basically before this, we had a kind of rule-based approach to like evaluating chess position. So what would happen, you'd have a chess engine like Stockfish, which basically you take like a team of 50 chess experts and a bunch of computer scientists, and they hard code, thousands of rules in to say how we evaluate every position. Whereas with AlphaZero, what it's doing is it's just given, here's an environment and here are the rules of the game, and you'll figure it out. Which is, so it's learning from scratch without any rules, and it's learning to create its own rules. And the thing with that is, I mean, I was watching last week. They did a big match between AlphaZero and Stockfish, Stockfish is like the the pinnacle of chess engines, and until AlphaZero came along, and they played something like 1,000 games. And in one of these games, like our understanding of chess, like before this, was like, okay, well, we want to keep all of our pieces. We don't want to give them away. And, it's okay to accept like a really ugly position because, the computer says that I can defend it, that I'll be fine. And what AlphaZero did in this game is he gave away, and this is like, just like, not he, but it gave away, 3 pawns, like right in the very beginning. And then it just slowly tucked all of its pieces into a corner. And like, the commentary, it's in this, there's a great book called Game Changer, which is by one of the people who worked on AlphaZero and like a well-known chess author. And like the chess guys were all shocked. They're like, well, what is going on here? And then you see 20 moves later, like, oh my God, like suddenly every move that Stockfish plays loses. Like it just suddenly turns into this brilliant strategic decision. And that's something that actually, like, in the last 2 years we've seen, like, has completely changed the way that chess has already started to, like, change the way that chess is being played. And the thing is we still, like, I've played chess for, like, a long time. I consider myself decent at it. Like, I used to stream chess, which, that's not a great qualification, but I used to do that. And, like, we look at some of the decisions it's making and we still have no idea why it's making those decisions. So if we were able to, explain long-term strategic choices made by reinforcement learning algorithms, that can further our understanding of whatever problem we're trying to solve, which is, something that's really interesting. So instead of using, like, our physics or our understanding of the world to inform the network, we would want, or to inform our model, we'd want, it would, like, we probably want at some point to be able to learn from the model, because one of the ideas is at some point is that it's learning things at a superhuman level, so that way we can, learn from it. And so, with the whole Norvig Chomsky debate, which is rule-based versus learning-based approaches, I think, we don't really know who's winning that debate, and I don't think there's a right answer. But I think we need to differentiate between the two sort of applications of this, which is either, like, AI is a science and we're trying to learn from it and we're trying to learn about it and understand it, versus AI as just a tool to use. And so I think that's, I don't know where I'm going from here, but
I think you're absolutely right. Some people even say that AI is a subfield of mathematics, which is kind of, definitely it is, but it's always a matter of debate, as you say. And I think there's no right or wrong in some sense. It all comes down to how you approach things. But there's certainly tools used in AI which are abused in a bad way, which should definitely be not the case. Also, what I wanted to ask you, David, who inspires you in the field of artificial intelligence?
So that's a good question. And so, I mean, the first person who really inspired me actually was one of my professors, who took it from, in a master's program, you don't really have time to go deep into anything. You're getting what I would view as like a highlight reel, or you're seeing the peaks. So you're seeing where, oh, well, we learn about random forest because random forest worked really well. We will learn about KNN because that's another algorithm that worked really well. But you don't learn about the math and the hard work and the thought process behind the people who developed these algorithms. And this professor kind of showed us is like, well, hey, this is actually like how we go about thinking about an algorithm and how we go about researching and finding new things. And so, that's what really set me from being like, yeah, I think I'm interested in this, to like, oh my God, I'm excited about this. That, and then there's a few researchers. So, obviously, like, I really like Jan LeCun and Yoshio Bingio and Jeffrey Hinton. Like, all those people are really exciting. But then, I think really it's just like, you could ask me this question like in a month and my answer would be completely different.
Yeah.
But it's really just whoever is like coming up with the most interesting papers, or not the most interesting ideas. So, like, I think the people who come up with, creative ideas, bringing in ideas from other fields, for example, bringing in ideas from physics into, into AI. So, like, if you asked me 2 months ago, I went to a talk before all this, before this pandemic happened. And the talk was on physics-inspired neural networks, which is, that's something I've never thought of. So basically, if you think about it in engineering, like, normally we do finite element analysis and things like that, which are a bunch of linear functions to estimate, like, a really complicated system. And if you look at a neural network, it's basically, it's a nonlinear estimator, right? So that means we can develop with less computational cost the same complexity of, a depiction of whatever system we're looking at. And what this guy this lab used it for was to take that and have it learn parameters to partial differential equations, like describing systems. And the idea is that, given a medium amount of data and like a bunch of physics equations, you can say, for example, from video feed of a hurricane, determine the air pressure at every single point in that image with the same accuracy as like a model from NOAA, which took 32 days to run, which is, totally cool. And like, I just think for me, it's really the interesting applications and combinations with other ideas of like the intersection between like, where theory approaches or where theory informs practice and practice informs theory. I think anyone who's researching into that is like, someone who I aspire to be like one day.
That's cool. Excellent. Do you think having studied something different than CS makes you a bit more open-minded towards AI and you bring other knowledge into the field? Do you think that's an advantage?
I think it's definitely an advantage. I think that's one of the advantages of this whole field is there's a whole bunch of people. Like if you go to, at the latest conference, which was virtual, they had like a physicist happy hour where all the physicists, like former physicists, would go and all talk about like switching from physics to AI, which is and I think that's something that makes this field so cool is you can have all these different knowledge bases mixing together. And for me personally, it's kind of changed my approach to understanding problems. So, for example, whereas, someone with a different background, I can't speak to them because I don't have their background. But when I approach a problem, from an engineer, like an engineer's perspective, is, you'll go in and you'll first want to get like a simple baseline or, the simplest minimal working example of something. And then you can iterate off of that. And then, you might want to design like little experiments so that proves that what you're doing works. And like approaching problems in, from an engineer's kind of methodical perspective versus, one of my friends comes from he's very artistic and he comes from like a web design perspective. Like, he worked as a front end developer before this.
Mm-hmm.
And when he's given a problem, what he'll do is he'll go and he'll just, think for a really long time and try and come up with like the most cool, like interesting, like elegant approach, which is very different from mine. So that way, when we work together, we end up like I'm making these, kind of ugly engineering approaches, and then he is making. And I apologize, he's not a front end developer; he's a full software engineer. But I view him as like a, kind of a creative, a thinker. But like I'll be just kind of like throwing things up on the board, and then he'll come along and say, "Oh, well, like what if we did this?" Like a week later, and then suddenly, well, like together we can like, I feel we cover each other's weaknesses, which is a really cool thing about this field is you can have a diverse group of people who end up working together.
Mm-hmm. That's so cool. So it was super interesting talk, David, about RL, XAI, and so on. I think we can go into more depth in the second part if you are more into.
Wow! It's already been 50 minutes. Yeah.
Yeah, into research and so on. Is there anything you want to touch on? Another topic maybe, and what the audience should know about?
Yeah. So one thing that I think, well, first of all, regarding XAI, if people want to work on XAI, I think there's a few things that you should know about. The first thing is, there's really 3 ways that you can work on it. So the first is, something that's an intrinsic explanation to an algorithm.
Mm-hmm.
So like, for example, with, decision trees or random forests, you have this criterion that you're splitting trees on, which you can estimate. Or with, in deep learning, you have attention, which you're basically like, in the context of natural language processing, you're computing the probability of, of a word occurring given all the other words. And with that, you can actually show like what words it's considering more important than other words. Which, that's a really hard area to work on. That would require, you to come up with a new algorithm. But then there's a couple of other ways of approaching it. Well, one is you basically change the inputs a little bit and see what happens. Which is, I think a really easy way to start getting into and trying to understand whatever you're working on. So, for example, in reinforcement learning, there's a recent paper that came out where what they'll do is, you have I'll just talk about it in the context of chess because, that's the reinforcement learning application that I know best is you'll have a position on the board and you'll see that like your algorithm made this move. And what you'll do is you'll take away one piece at a time and see whether or not that changes the best move. And from that, you can see which areas of the board it considered the most important in making this decision to do that thing, which is, so that's perturbing the inputs. And then the last main way of doing this is to take, you have a very complicated black box model, such as, a deep neural network. And what you do is you train that, you have it running fully, and then you take some sort of simple model. So like you take linear regression or logistic regression, and you train it to learn what the neural network does, which is pretty interesting too. And from that, then you can suddenly see like, oh, well, like if my linear regressor is saying that this feature is important and my linear regressor is estimating this very complicated model, that's probably what my complicated model is thinking too, which is, so I think that's something, it's not like a very hard area to get into, but it's a very, difficult set of problems because, even all of these things are estimating things at a very high level, which we would like a much higher level than we would want to, or not higher, a shallower level than we would want to approach. Let's see what else. I mean, I can talk for a long time. The other thing that I'd, really like to talk about, which we might save for another time, is, this idea of, I was telling you about it a little bit of myoelectric control and like basically the intersection between, AI and prosthetics, which is, a really cool area, but that can be up to you if we want to talk more about that.
Sure. I mean, go into depth a little bit, how it works.
Oh, yeah. Okay, so basically, we'll get into, so basically we're talking about, so with the term is myoelectric control. And what that means is, so myoelectric, or it comes from electromyography, which is the measure of signals so that come from the brain and the rest of the body. So basically, let's say I want to move, like, wave my hand. I won't actually think it, but my brain will say, okay, it's time to wave your hand. And what it's going to do is it sends an electrical impulse through the nerves. And that electrical impulse goes to, a special type of, muscle nerve intersection called a motor unit. And it hits a special type of muscle called a myocyte, which then contracts. So, one thing, this is an experiment you should try at home, but if you've ever been shocked before, your muscles, sometimes you can't let go of whatever's shocking you. That's the same sort of thing that's happening, is the electricity is causing your muscle to contract. And that's the same way that, you move. And what you can do is if you take these signals, right, because they have to get from point A to point B, they have to get from your brain to, your hand. And if you can measure these signals, you actually have a direct measurement of your intent, of what action you're trying to make. And so the idea of, myoelectric control is that, let's say, like heaven forbid, like I lost my hand. If we measure these electrical signals in the upper arm, what we can do is if we train, for example, a classifier on them, and we learn what, waving my hand looks like in terms of signal, we can then make that, so we can sense it here, make that prediction, in like some sort of embedded chip in the prosthetic. And, in almost real time, you have a hand that moves with your thoughts, with what you want to do, which is really interesting. And, there's a lot of really interesting things about it. So, for example, one of the difficulties is you can't really train on, like, you wouldn't think that you could train on a, no hand, right? You wouldn't think that you could give a label to tapping your finger when you have no fingers. But that's actually one of the really interesting things is when you lose a limb, the nervous connections, like, more or less remain the same. So what they'll do is they'll take a sensor and they'll have you sit it like a computer, and the computer will say, okay, like, think about tapping your fingers. And, by thinking about tapping your finger, like, moving your index finger like this or grabbing something, you can actually generate the same connections. And then you can train on that and put that in a prosthetic hand. And then, you have 70% of the functionality of your hand, which is, totally cool. I mean, there's a lot of room for optimization. So one of the problems, one of my big gripes with this whole thing is the fact that it uses like a classification algorithm, so that we have to have labels to actions at all, which, this is one of the really interesting applications of reinforcement learning. So last year, there was a really cool paper that came out, and it was in prosthetic feet. And what they did, it wasn't reinforcement learning, it was imitation learning. So which is somewhat related, is so they take, a deep neural network or something similar, and they give it a bunch of examples of people walking, and it learns to behave like them.
Mm-hmm.
And then you embed that in a prosthetic leg. And what they showed was, which is really amazing, is that the leg, the feet have to walk, a special way depending on what the type of what surface you're walking on. And they only showed it examples of people walking on flat surfaces. And then they put it in somewhere in a prosthetic, and they had it walk up a hill and walk up rocky terrain, and it learned to generalize just well with that, which is, that's really cool. The other thing is they can take it and they can actually make these predictions. I think it was 300 times faster than real time, which what that means, the implications of that are totally amazing. So that means basically we could do further optimization. So you would be able to actually augment human capability with this sort of technology, which is, super futuristic. I think my dad always talks about the $6 million man, with its whole bionic body. So you could completely optimize, walking or anything like that, which is, I think that's really interesting. And, I think in the problem with this whole field, so yeah, I think reinforcement learning is a really interesting application, especially, in that where typically supervised learning is used. And I don't know. Yeah. So I think, I don't know. I really love that whole little subfield. And again, I think you've had Miguel, when he was on here, talked about, the intersection of robotics and AI. And I think that's just such an interesting subfield, especially if you can combine it with, humans, which are also really interesting.
It's kind of hard to do everything at the same time. How do you keep yourself up to date, in terms of papers, news about air, because the field is so fast in terms of movement?
Oh yeah. So, I mean, it's hard for sure. The main thing, actually, the whole reason I got on Twitter, so up until about a year ago, I was like, oh, Twitter is useless. Why would I do that? I don't have anything, interesting to share. I'm sitting at my computer. And, but following, researchers and authors I liked was what, it's moved beyond that now. but that was why I got into Twitter, was to follow, people who I think are interesting, which is one way. And then the other thing is really just having a group of friends who are also, from different backgrounds than me, but also excited about it. And, if each one of us, if I find 10 interesting things a week and someone else finds 10 interesting things a week and we share them, I've now found 20 interesting things a week, and I don't have to read all of them because, someone else has already talked about it and summarized it for me. But, it's really hard. One thing I'm glad is that I'm glad I don't work on natural language processing, because, I was talking to one of my professors. He's an adjunct professor, so he also works in industry, and he's saying oh yeah, I probably read 20 papers a day just to stay afloat. Oh my God. But I think it's hard, but as long as you have, as long as you're connected to the community of people, you can also parse what's important. And I think the other thing to remember is, since there's so much research, you have to learn, I have a professor, he says as soon as you graduate, everyone's looking for a reason not to talk to you. If you go in with the assumption that this paper is junk and the authors have to prove it to you, and that's kind of mean, but that can save you a lot of time if you come at it with a more cynical attitude. You can say oh, well, I actually shouldn't be going past the abstract and conclusion of this paper because it doesn't mean anything to me, or I think this idea doesn't make any sense.
Yeah,
Like,
got it.
yeah.
Speaking of Twitter, you also have a blog. Where can people find you to wrap things up for the closing of this podcast?
Oh yeah. So my blog is at josephdavid.github.io, which, with me working on, finishing my master's project, it took a hit this last 6 months, but expect a lot of blog posts soon since I'm, locked at home with nothing to do. And yeah, so I'll talk about, whatever my interest of really the month or week is. So anything from, talking about, that's how we connected with my blog post on Explainable AI, to, time series, which is, another topic that I love, to building like reproducible data science environments. So, I mean, really anything that like whatever wind blows past me, it could be covered on the blog.
Sounds amazing. David, thank you so much for taking the time. And I think we discussed so many topics. Unfortunately, we only scratched the surface. But I think the more you get into the field, maybe we can do a second part, as I mentioned earlier on. And hopefully we'll learn more from you in terms of reinforcement learning / robotics maybe in the future. Again, thank you so much, David.
Yeah, thank you. This was really fun.
Awesome.